What I was discussing, the Dijkstra's shortest path. Huh? এটা ডিসকাস করছিলেন ডিএফএস Okay. So today, first we'll be discussing these shortest path algorithms. And this is the famous shortest path algorithm, single source shortest path. Okay. So from a single source, say this could be a source, or this could be a source, or this could be a source. You fix the source. Okay. Say for example, you are fixing the source here. Okay. And then from this source, we have to find out what is the shortest distance of all the nodes. Okay. So this is called the single source shortest path problem. And here there is a famous algorithm credited to Dijkstra. Okay. So this Dijkstra is having many more contribution in computer science. Okay. He developed other algorithms also, but this is the most famous one. Okay. So you have got this graph. And you see this, this is the source node. Okay. So this is our source node. And how to find out? So these edge weights are given. So this is a directed graph. Directed graph where we have seen the undirected graph like this, where we do not have direction of the edges. Whenever we will be having direction of the edges, that comes in many different applications like this. Okay, say this is a communication network maybe. Okay, so this node or a traffic network, this node is say Durgapur, and then this node is say Panama. This node is Rajbath, like this. Okay, and this edge weights are the distance, and this is telling that there is a way from source to this guy, this city, directly we can reach. And from here to here I can reach directly, and the edge cost is 10. But there is another path from this to this via this node. Okay. And via this node I can also reach here. And you see clearly that if I take the direct route, if I'm routing from here to here, then the distance or the cost that will be involved is 10. Okay. Maybe 10 rupees in terms of fuel consumption. Okay. But if I take this via path, then I am having 5 plus 3. 5 cost here and $3 costing here. So with $8, I can reach from here to here via this. So this is the fundamental building blocks of analyzing this shortest path problem. Okay. So that means we are having a path here to here, but once I have got this node, okay, then I'll be trying to see that from here via this node whether I can reach here. Okay. So that via calculation may be updating our shortest path. Okay. So this is the building block of this problem, shortest path problem. Okay. And this is a natural idea. If that would have been discovered right now, we would have gone like this way. So Dijkstra was lucky that he was at that time nobody discovered. Okay. So it's a quite natural idea that whenever you will be trying to find out from here to here what is the shortest path, say your objective function is that the fuel consumption you will be measuring. Okay. Then from here to here, if you are having some path and there are some other paths also, so you have to check all possible paths, right? And then we have to compare all the cost involved in those paths and whatever is the minimum that I'll be taking. That will be giving the shortest path. Okay. This could be distance also. So if I am taking the direct path, that is taking 10 kilometers. But if I take the via path, then it is costing, say, 5 kilometers here, 3 kilometers here. Okay. So now this is the shortest path problem. How Dijkstra solved this? Okay. So that we have to understand here. And one of the constraint is that okay, if I am having some kind of negative cost here, okay, right. So the negative edge cost, if I am having, the Dijkstra's algorithm is not fit for that. Okay. There are other algorithms. Okay. That is taking this negative edge cost and solving that problem. Okay. So this Dijkstra is fit for whenever all edge cost is positive. Okay. Now this is the simplest graph say I am talking about. Say if I am having some negative edge cost, okay. If I am having some negative edge cost, and say I am trying to solve this problem, say the Dijkstra's algorithm, I'll be trying to apply Dijkstra's algorithm, and I know that each edge cost should be positive. Okay, right. And then what I am doing is all these edge cost I am making positive first, and then I'll be applying the Dijkstra's algorithm. I don't know yet what is the Dijkstra's algorithm. Only I know the Dijkstra's algorithm is applicable whenever the edge cost is positive. Okay. But if I am having some negative edge cost, then you can argue that okay, sir, we can convert this negative edge cost into positive edge cost, and then we can apply the Dijkstra's algorithm. Okay. So let us see whether this idea is applicable or not. Okay. Say there are two paths from S to U. One is like this, and the edge cost is given. Okay. And another is like this. So maybe I'm having this is our T, this is our S, this is our E. Okay. And another path is this S to T, and then T to say W, and then W to U. Okay. So this may be the graph structure. Okay. So this is -3, this is 5, and this is -3, this is 1, and this is 3. So this is W, this is U. Okay. This could be the structure. Two paths I am having. So one is this, and another is like this. Okay. So these two paths I have dissociated and I have written like this. Okay. Now if I adapt that idea that okay, we'll be converting each edge weight as positive. Okay. Then what I can do, I can for this, I can add up for this and for this. What I can do, I can add up +3, and then I can make it. So if I am not converting it, the edge weights, then what will be the shortest path? S to U, whether this path or this path. If I am adding, then 5 minus 3, 5 plus -3, that means 5 minus 3, that is the path cost is 2. And here the path cost is 3 plus 1 minus 3. 4 minus 3, that is 1. Okay. So this is looking like, if I am not converting, this is looking like that this is the shortest path. Okay. Are you with me or not? Are you with me? Huh? You? What is your name? What is your name? Sushant. Huh? Okay. What is your roll number? 107. Okay. So you are having two paths, right? And then this, I am getting that this is the shortest path. If I am not converting, if I am remaining the negative weights as the edge cost. But now you see, I am converting it into positive one, each edge cost. So this will be, if I am non-negative quantity, if I have to, that means greater or equals to 0, then definitely I have to add up 3 here. So that I have to add up this, so it is making 0 and it is making 8. Right? So what will be the shortest, what will be the path cost at this moment? 8. Now you see, so remember before doing this, this was the shortest path. Okay. Now I am converting each edge weight as positive. So now this is 3, this is 3, this is 3. So it is 0, this is 4, this is 6. Okay. So what is the edge cost? 10. Now you see, whenever I am converting that idea, whenever I am converting the edge cost as positive with that idea, right? Then which one is becoming the shortest path? This one. Okay. The shortest path is changing, but that is not in realistic situation. That is not the case. Okay. So you see this with this counter example, we can say that our simplistic idea that okay, even if the edge cost is negative, but we are trying to convert it into positive one, then I'll be applying the Dijkstra's algorithm, because the condition, the precondition is that okay, all edge cost is positive. Then it is fitting always. Okay. Dijkstra's algorithm. Okay. So if this thing is coming, then you should be giving this counter example. That okay, no, this idea is not good, right? Okay, now we are moving to this Dijkstra's single source shortest path algorithm. Okay, before that, we have to, this is relying on this relax procedure. Okay. This is from CLRS, this figure. Okay. So the thing is that what is this relax procedure? That means if say this is some node, and whenever I have discovered this node, okay, from the source I have come up here. Okay, I have discovered this, and whatever is the shortest path I have calculated in an incremental fashion. And then suppose I have got this, the shortest path from this source node to this, okay, that we are denoting by, say this node is u, that we are denoting by u dot d, the shortest distance from the source node to that u, okay, that we are denoting by u dot d, that is the CLRS notation. And say this is 5, say. Okay, and before discovering this, some other node, some other way I have reached to this V, okay, and that from source to this, and that was V dot D. V dot D, say that was 10, okay, some other path. Before discovering this, I already got this, okay, right. Now once I have discovered this, I am seeing that from here to here, I can go with a cost, with some cost, say 3. Okay. So now you see, we will be using this relax procedure. That means via this u, whether there is any path to v or not, and if there is a path, then what will be the cost involved from this u to v from this source node. Then I am getting what? From source node I can reach u, and then I can, from u to v, I can go. That means from source to v, I am having a path, via path with u. Okay. Whether, so far from source to u, say I have got 5, and then u to v, I have got 3. So from source to v, how much I am getting the cost? 5 plus 3, that is 8, right? But before discovering this, I had some other path to this v, and that was 10. So via this u, I am seeing that I can reach from S to V in a less costly way, right? Previously it was 10. Now via u, I am reaching to V with cost 8. Okay. So then what I'll be doing is, so here this condition I am checking, that V dot D was 10 in our example, V dot D, and this U dot D was 5, and then WUV was 3. So whether 10 is greater than 5 plus 3. Yes, that means previously how I am reaching from source to this V, that was 10. So that was more than what I have discovered now. Okay. Then what we got to do? We have to update the shortest path. So that is exactly I am doing v dot d. Now v dot d will be u dot d plus wuv. That means I will be going from source to v now through via this u. Okay. And then v dot pi will be this u. That means how I am reaching v right now, I am reaching v through u with this shortest path. Okay. So there will be a parent pointer that will be, so that we can maintain. Okay. So this parent pointer will be giving, we will be getting the shortest distance. Okay. But if I have to trace that shortest path, then this parent pointer will be helping us. Okay. So this is the fundamental building blocks of this relaxed procedure, of this Dijkstra shortest path algorithm. And this is called the relaxed procedure. That means if a node is discovered, via that node, whether I can reach to its adjacent nodes with a less costly way. That is the main idea. Okay. So now this is the Dijkstra's algorithm. Okay. Very simple algorithm, right? So first we have to initialize this single source. We have to initialize this. That means that you are seeing that S node S, that is the source, that will be initialized with 0, and all other vertices we haven't computed yet. So the distance from the source, I'll be assuming that they are infinity. Okay. So that is the initialization procedure, and that is exactly we are doing. So 0 here, source node, source to source, we are not moving anything, so it is 0. Okay. And then from all other nodes I haven't seen yet. Okay. So that's why I'm assuming that they are having a very large cost. Okay. So this infinity you can take as value, say whatever the each cost you are sensing, more than something. Okay. Say 10,000. Okay. During the implementation you can do this. Okay. And then this we'll be maintaining to list this S. That means this the vertices that will be in the shortest path. Okay. And then we'll be maintaining this queue. One queue we will be maintaining. Okay. Right. And this is one priority queue. Okay. And one thing is that, okay, this queue during this initialization process, we have to make this queue also. That means this S will be here. S is having cost 0, so it will be at the front of the queue. We can think of, okay, because this will be extracted right now. You know the queue property, and if we can implement this with min heap also, okay, so that will be at that time in the root min heap. We have to extract this node, okay, first, and then other we can sort of, others are all infinity, so we can take it in lexicographically we can take. So first maybe t, then x, then y, and then z. Okay. And then while q is not empty, so here I am saying q is not empty. So what we got to do, we have to do u equal to extract min q. Okay. So we have to extract this guy, and then we have to put it into this. So this is small s, and this is capital S. This is small s. Okay. So we have to take this here, And then what we got to do is, once I have discovered this node, I have to check that via this node. So this will be our U in the relax procedure. Via this node, all the adjacent nodes I can reach via this node in a less costly way. So that means we have to call this relax procedure. So there's this here, U is this S, small s, that is the source node we have discovered now. And this V is all adjacent nodes here, T and this Y. Okay. And this weight of this UV is given. Okay. So first I am taking T. And you see the relax procedure, U is S, and what is V? Can you tell me? In this, if I am taking this, what is V? Which node will be V? T. T. This guy is, so we had node U and this V. Okay. Right. So this is S and this is T. And you see, so T dot D, that means V dot D. What was V dot D previously? Before discovering this node? So it was a large cost. Okay. So V dot D, right? That means T dot D. What I got to do, I have to check this condition. V dot D is greater than U dot D. What is U dot D? U dot D, U is what? S. S dot D, 0. Plus, what is WUV? 10. So that is 10. Okay. And what was V dot D? It was large cost. So V dot D is greater than this 10. Then what I got to do? I have to update that V dot D. Okay. So V dot D means T dot D. So from source to T, I know that from the source to T, I am having a path. Okay. And V dot D will be equals to U dot D plus WUV, that means 10. So this infinity now will be replaced with 10. Okay. So similarly, this Y, so this for each vertex V adjacent to U, U is this S. So adjacent to this U, from the adjacency list representation, I'll be getting which are the nodes which are adjacent to this U. And then this guy will be replaced with how much? Huh? 5. Okay. Right? So it is extracting the minimum weight of this vertex. So that the distance. We are maintaining this distance. Okay. Next we will be going. We have to update this queue. Okay. So here I have got this T as 10, isn't it? And X as, no, X is still infinity. And this Y is, this is Y. This is why perhaps it is not visible. Right? Now visible. This is Y. Okay. So this is Y. This is our X. This is our Z. This is our T. Okay. Getting? Now little bit I have to So now this Z is what? Z is how much? From U, I don't have any adjacent connection to this Z. So this is Z. So will it be at this moment with this for loop, when this S is discovered, will it be updated? No. So what will be Z? Okay. So now this thing, that means Q structure will be, so this Y will be at the top of this, right now this here. Okay. So this Y will be here, and then this T, then X, then C. Okay. Something like this. And I'll be going to this while loop again. While Q is not empty, Q is not empty. Okay. Then what I got to do? We have to extract this U. The minimum is Y, and this Y will be in this list. Okay. Right. And now you see this, once I have discovered this Y, so this will be our, in the relax procedure, this Y will be our U. Okay. So this is the node via which I have to check whether from source to via any other nodes via this Y I can reach in a less costly way or not. Once I am discovering this Y. Okay. Right. Hello, are you getting? You getting? Huh? why why Y is in the first place in this queue? So it was in the third place. Why Y came up in the first place? Can you tell me? Listening or not? Huh? Why Y is taken in the first place? We are maintaining what? Hmm? Why Y is in the first place? Okay, what is your roll number? Huh? 159. Your roll number? 1? 180. 130. Okay. So this Y having the minimum of all. Okay. All these nodes which we can reach from this source in a minimum, in a less costly way. Okay. So Y is the minimum one. Okay. So that's why we have to take this minimum. This is a greedy algorithm going on. Okay. Always I am taking the minimum cost of the vertex from the source. Okay. And and this is the greedy algorithm because I haven't seen the other networks. Okay. I am taking the decision locally. Okay. Okay. Whatever is the minimum that I am taking. I am not checking all possible combination like the dynamic programming does. Okay. Just whatever is minimum I am picking up, and then let's see what is happening. Okay. Okay. So now you see this Y is discovered, and this I have to check that, okay, from this I am seeing that from this to this V, that means it's adjacent vertices. I have to relax. Okay. That means via this y, whether I can reach to its adjacent vertices in a least costly way. Okay. So these are the three adjacent vertices that I have to take. Say I am taking this one first. Now this y and this is our t. Okay. And once this y is discovered, that is our u. Okay. That is our u. And this t is our v. Okay. T is v. U is our y. So via y I can reach v in a less costly way or not. So previously I reached v with how much cost? 10. Okay, so that was the direct cost, okay, from S to V. Okay, direct path was there. So V dot D is 10. Okay. And what is this U dot D? U dot D. U dot D, that means Y dot D. That means the from the source vertex to that Y, what is the cost? 5. And then what is WUV? That means WUT, YT. WYT is 3. So it is 3. So that means 8. Okay. So I am seeing that V dot D is greater than this 5 plus 3, that is 8. So I have to update this V dot D with this cost. That means the cost of this, instead of 10, it will be now 8. Okay. And then this V dot pi will be U. Okay. What is U? U is Y here. Okay. So previously this was the parent pointer. Okay. That means that was the from S to V, I was reaching with this path. That means this was the parent pointer. Okay. But now we have got that, okay, via this Y I can reach here in a less costly way. So we have to remove this parent pointer and we have to give a parent pointer here like this. So V dot pi will be equal to U. That is the implication. So that parent pointer will be guiding us. So from here to here, that was another parent pointer. So if I am tracking which is the shortest path nodes on the way from S to V, S to T, then I'll be getting that, okay, this V will be there, this T will be there, and then I am tracing back here, okay, then Y, and then S. So this is the nodes on the way from here to here, the shortest path so far. Okay. Finally, maybe one shortest path could be this. That could have been also the case. Okay. Okay. So this is the way. So now this guy from here to here, you see. So this was 5, and then this direct cost was 9. So 9 plus. So this will be, once this I have discovered this. So this will be 5 here, and then what is this? 9. Yes. So this will be, I guess, 14. So from here to here, once I have discovered this, I have to go from here to here. Okay, I can also reach. So with this relaxed procedure, so it was V dot D, V was Z, V was X. This is X, right? So what was that? So this is our U, this is our V. So what was V dot D? V dot D. Once I have discovered this, I am trying to see that, okay, via this I can reach here. What was that? What was that? Infinity. large cost. Now what is u dot d? 5, and this is 9. So 9 plus 5, 14. Okay. So in this case, this x will be, so this x will be, its weight will be 14. Okay. Right. And then this, again I can reach from here to here. Okay. What will be the cost of z? 7. 5 plus 2, 7. Okay. So I guess this will be, this is again with some other cost. So this 13 is, they have taken another. So once I have discovered this, then that is another way of reaching x. Okay, so that's why this is 13. So it will be 14 here, okay, initially. And then once I will be discovering this 7, I can go to this via this 7 in a less costly way. So instead of 14 at that time, it will be 13. Okay. So this, I have discovered this. I have got its adjacent vertices. Okay. So that means this is 14 and this is becoming 7, right? So this y is here, and then what is this t? T is what? 8. What is x? 14. What is z? 7, right? So now this I have to again, I have to take it in this mean heap form. 7, maybe 8, and then this 14. Okay. So 7 should be there at the root. Okay. And then this 7 will be taken up. So this 7 is taken up next. And then we have to check whether it's adjacent vertices. Okay. We can reach from there in a less costly way. Okay. So like this way, we have to keep on updating the list. And once you see this, all the adjacent vertices of this is taken into consideration, it is blackened. Okay, right? So, so that is the way we this Dijkstra's algorithm finds the shortest path from single source. That means from this or from this or from this or from this, whatever you fix a source vertex, and from this source vertex, I am trying to find out the shortest path of all these nodes. Okay. So you complete this graph after going through this algorithm. So this is the way we have to proceed. Okay. Okay. So today after this, maybe I can take one online class. Okay. Extra class.